Um, Good afternoon, ladies and gentlemen. Thank you all for being here with us today. First of all, I would like to thank Professor Malek and Professor Strakosh for giving me the opportunity to host this event, which is organized by SIAM Student Chapter in Prague. Today, we are very honored to welcome a very special guest, Professor Cleve Moler, who is with no doubt a living legend. I believe it is totally obvious and people know who he is and what he has done. As you all know, he is the creator and inventor of MATLAB and co-founder of MathWorks. Professor Muller is one of the author of LINPACK and EISPACK scientific subroutine library, as well as author and co-author of several textbooks on numerical analysis and computational science. He is also a member of the Association for Computing Machinery. And last but not least, he was the president of the Society for Industrial and Applied Mathematics during 2007 till 2008, and he continues supporting SIAM by being a visiting lecturer. And today he will be sharing with us his expert opinion on how SVD will save the universe. Before I ask Professor Muller to start his speech, I would like to mention if someone has a question during the talk or after, please leave them on the chat box and we will discuss them with Professor Muller at the end. With all that, please join me in welcoming Professor Muller. Professor Muller, please, the floor is yours.
Well, thank you very much, Janine. I'm very pleased to be visiting you. I wish I could be in person. I hope we can do that someday. I'm a big fan of the singular value decomposition, and I want to tell you about it. The title about saving the universe will be explained in a moment. When I first heard of the singular value decomposition, it was purely theoretical. When I was a graduate student at Stanford years ago, I worked with George Forsyth. He started the computer science department at Stanford. And we wrote this book, and this SVD is mentioned in the book, but we didn't know how to compute it. And one day at a seminar, Forsyth said, will somebody figure out how to compute the darn thing? And Gene Golub did. Golub was a new professor at Stanford, and with Velva Kahan from Berkeley in 1965, he developed the algorithm for computing the SVD that essentially is still the one we use today. And then in 1970, Christian Reinsch in Munich wrote some algol programs and that described the method. Golub is famous for many things, but he was proudest of his work on SVD, as his California license plate indicates. In 1976, I was a professor at the University of New Mexico in Albuquerque, New Mexico. I spent a day a week at the Los Alamos National Laboratory in the mountains north of Albuquerque. I worked on their subroutine libraries for their supercomputers. And at that time, I made a film, actual 16 millimeter celluloid film. If I had an audience, could I see the audience, I'd ask you how many of you have actually seen film. There was two reasons to make the film. One was to promote the singular value decomposition, which, as I said, was brand new at that time. And the other was to work with the Los Alamos graphics libraries. Los Alamos was important work on computer graphics at the time. You're going to see this film I'm about to show you. It looks very crude by today's standards, but at 1976, this was very innovative. with three-dimensional hidden lines and even text with Greek letters. So let me show you a piece of that film. Where is it? I think this is it.
The computer is used to simplify the matrix so that most of the entries will be zeros. One method is known as the singular value decomposition. The original matrix is represented as the product of three matrices. In the second of these matrices, the only non-zero elements lie on the diagonal. The other two matrices must preserve the properties of the original matrix, so they are orthogonal matrices. Each is the product of elementary matrices, which affect only two rows or columns. Scientists at Los Alamos Scientific Laboratory have been studying methods for the accurate and efficient calculation of the singular value decomposition and of describing to computer users how the computation is carried out. In this three-dimensional representation of a small matrix, each pyramid depicts the magnitude of a single matrix element. The diagonal of the matrix runs from the upper left to the lower right. Orthogonal transformations will be used to introduce zeros into the matrix. The initial transformations put zeros into the first row and then the first column. Each transformation affects two other columns or rows, shown here in blue. Later transformations introduce zeros into later rows and columns, while zeros all remain. The second stage of the calculation is a repetitive or iterative process, which reduces the size of the remaining off-diagonal elements, but does not zero them in a single step. The calculations now being shown are primarily intended to reduce the size of the off-diagonal element at the lower right-hand corner. Once an off-diagonal element has reached a negligible magnitude, it is set to zero. The computation of the corresponding diagonal element is then complete, and the resulting singular value is shown in blue. The final diagonal matrix, together with the two transforming matrices which produced it, then provide the basis for a complete analysis of the original matrix and the system which it models.
Well, if you've never seen the singular value, some idea of how we compute it, and the whole that's just part of the film. The whole film is 6 minutes long. If you want to see it, if you're interested, just Google Moler SVD, and you will go to this YouTube link. That was not done with MATLAB. MATLAB didn't do graphics then, but here is a recreation in today's MATLAB. Shortly after I made that film, the producers of the first Star Trek movie came to Los Alamos because they wanted to get graphics to show on the screens in the Enterprise in the movie, and Los Alamos was a forefront of computer graphics. So the first Star Trek movie came out in 1970, is threatening to destroy the universe, and Star Trek comes to the rescue. I'm going to show you two clips out of that movie. Look over Spock's shoulder. Oh, there he is. Okay, that's just a still clip. So you can see that Spock is using the singular value decomposition on his scope as they save the universe. Let's do the videos. Here's one of them. Oh, that was a short one.
Just enough for us to break free.
Break free to where, Commander?
show of resistance would be futile captive. The computer is used to simplify each.
So that's just two very short clips out of the, and you can see that Spock is using it to save the universe. So the opening screen, MATLAB, it was not a programming language. These are all the functions in MATLAB. It was just a simple calculator with these 80 functions, but one of them was the SVD. And that was the first time many people had access to code that would actually, here's how you get it in MATLAB. Any matrix A, big matrix over here, not necessarily square, is the product of three matrices, U, S, and V transpose. The S is diagonal. S are orthogonal. Orthogonal matrices are we love them in numerical computation because they don't magnify errors, they preserve angles. It's great when we can do anything with orthogonal matrices. Here's the 2x2 example. On the left is an arbitrary 2x2 matrix, 4 elements. On the right is its singular value decomposition. U and V in this case are just rotations, as you saw in the movie. With it, there's a single angle there, and then the two singular values are on the diagonal of S. So there's 4 unknown quantities on the right, and they can be match the 4 unknown quantities, the 4 known quantities on the left. And this counting argument continues for larger matrices. Here's a way to look at it geometrically. The matrix A is a transformation from one space to another, and it gets decomposed into 3 transformations. U and V are generalizations of rotations. One rotation in the domain, another rotation in the range, and then with the new coordinate system, the transformation is a diagonal matrix. Let's look at an example. Here's a matrix of order 8. At first, it just looks like a bunch of integers. But you see that why is it 260? That's because if you take the numbers from 1 to 64, add them all together, and then distribute it over 8 columns, the sum has to be 260. If we ask for the singular value decomposition of A and then look at the diagonal of S, then the largest singular value is 260. Why is it 260? If I was giving out homework, that would be your homework for today. Show that the largest singular value of any magic square is the magic sum. This matrix, now that's true of any magic square, but this matrix just has 3 non-zero significant singular values. The other 5 are all on the order of round-off error. That isn't true of all magic squares, but it's true of the ones that are order is a multiple of 4. Here's the plot of the singular values versus their index. We've ordered them, and not 3 of them are non-zero, and the other 5 are all 0. We will see more plots like this with more singular values, but this is what we're interested in, when the singular values decrease rapidly with their index. Those 3 non-zero matrix singular values make the rank of the matrix 3. Here's the first three. I'll talk more about rank in a minute. Here's the first three columns in U. Those columns are perpendicular to each other. Here's the three singular values on a 3x3 matrix now, small matrix. And here's the first three columns of V. Again, they're perpendicular to each other. And if I multiply U times S times V transpose, I don't get back to exact integers. There's some round off error. But when I round that product, I get back my original matrix. So that 8x8 matrix can be expressed as the singular value decomposition with only three columns in U and V. Here's another important decomposition called the principal component analysis. This comes out of statistics. If you have some data which expresses, say, height as a function of weight, you make a change of coordinates, center the coordinate system in the data, and then in the new coordinate system, you can have principal components, orthogonal directions. The black one is the first principal component. The yellow one is the second principal component. And with just a couple of these components, you can explain your data. In statistics, the output of the PCA involves terms called coefficients and score and latent roots. I won't get into what they mean. The SVD and the PCA are closely related. And in 2006, I wrote in our newsletter that the Wikipedia pages of SVD and PCA didn't mention each other. And Wikipedia was updated within a couple days so that there was cross-references. Here's how you'd compute the PCA if you didn't use the singular value decomposition. This is a matrix, a MATLAB function that computes PCA and doesn't use SVD. You start by subtracting the mean from each column. You have some data X, and you subtract the mean of each column from that column. This is called centering the data. And now the mean, the average of each column is 0. And then you compute X prime times X. If you have 10,000 observations on 10 variables, then X has 10,000 rows and 10 columns. But X prime times X only is 10 by 10. All the data in X gets squished together into the covariance matrix C, and then you compute the eigenvalues and eigenvectors of the covariance matrix and read off the statistics. I have a hard time saying that word. Read off the statistical quantities from that singular value decomposition. So that's how you see PCA explained most of the time, as it's the eigenvalues of the covariance matrix. Here's how you compute it if you do have the singular value decomposition. Again, you center the data, and then you take the SVD of that directly of X. You don't form X prime times X. And you can read off the statistical quantities from the SVD. This has the advantage numerically of preserving the small singular value. Now, if we're doing PCA, we're not interested in the small singular values, small components, only interested in the large ones. But sometimes it's important to know the small singular values as well, and they're preserved by this. Forming X prime times X clobbers the small eigenvalues. So SVD originated in my world, in the world of matrix computation. It's more reliably numerically. The PCA had its origin in statistics as the eigenvalues of the covariance matrix, and it loses the small eigenvalues. Here's a short course in linear algebra. As Gil Strang, a friend of mine, is a professor at MIT, likes to draw this picture. You have a transformation from n-dimensional space to m-dimensional space. In Rn, there's two orthogonal subspaces, the row space and the null space. In Rm, there's two other orthogonal spaces, the column space and the left null space. And actually, if Strang was drawing this accurately, the width of this rectangle would be equal to the width of that rectangle. That's because of this fundamental theorem that the number of independent rows in a matrix is equal to the number of independent columns. That's actually a subtle fact. It requires proof. And this dimension is called the rank of the matrix. Here's a MATLAB function that computes the rank of A. You take the singular values of A, and then you count the number of them that are bigger than some tolerance on the order of round-off error. So in exact mathematics, the rank is the number of non-zero singular values. In computation, it's the number of non-negligible singular values. And in terms of the SVD, here are Strang's four fundamental subspaces. The first, if R is the rank, the first R columns of U and V are the basis for the column space and the row space, and the remaining columns of U and V are the basis for the two null spaces. So there's your course in linear algebra in 3 slides. If I write the matrix as U sigma V transpose and order the singular values in decreasing order, they're all positive. Now I'm going to make sure that sigma 1 is the largest, and I take this outer product, the kth column of U times the transpose of the kth column of V. That's the product of two vectors. This is in the wrong order. Usually when we take two vectors, their product, we take their inner product, their dot product, and get a scalar. But in this case, the outer product produces a matrix. It's a matrix with only one independent column, so it's rank 1. And A can be expressed as this sum of weights of the E's. And the error you make by truncating this approximation at any rank, at any number R, doesn't have to be the rank. If you, in the 2 norm, the error is the first term you leave off, and then something called the Frobenius norm, the error is the square root is the sum of the squares of all the singular values you ignore. This is called the Eckert-Young theorem, and it's a basis for what we're about to do. Here's a picture, cartoon picture. You have any old matrix on the left, and it's the sum of these things that are supposed to look like rank 1 matrices. We like to show this with image compression. Here's a JPEG of Jean Golub. It has 1,000 rows and 600 semi-columns, but it's a 3-dimensional array because there's 3 colors. And if you put the red, green, and blue components alongside each other, you end up with a matrix with the same number of rows, 1,000 rows, but now you have 2,000 columns. And I'm going to take the SVD of this matrix and use it to approximate the picture of Jean. And here they are. I'm increasing the rank. It's shown up at the top or up to 20. We're going to go to 50. By the time we get to 50, we can read the mathematics on the board and see Jean's shirt. Here's the original matrix. I'll go through it again, and you can't tell the difference on your screen between the matrix of rank 50 and the matrix of rank 1000. You can still see Gene has a checkered shirt at rank 50. Here's why that works. This is a log plot. The scale on the left is logarithmic, and it shows the singular values that drop off, just like they did for that magic square. Only here there's 1,000 of them. And by the time we get to 50, rank 50, the singular values have decreased by more than 2 orders of magnitude. And so the approximation of rank 50 is good to 1%, approximating the original matrix. Here's another example. I did this some time ago, but it's becoming even more important today when we talk about the control of the United States Senate. I'm not going to worry about who controls. Here's how the parties have controlled the Senate over the last 30 years. I'm not going to worry about control of the Senate or who's going to win the election, but I'm going to be concerned about partisanship. So in partisanship, I can go to this website, and on this website are all the roll call votes that are taken in the United States Senate over the last 30 years. And I'm going to make up matrices which are mostly minus ones and ones. It's -1 for a no and +1 for a yes. There's some zeros in the matrix if a senator is missing or abstains or is out running for president or something like that. So the number of rows in these matrices is usually 100 because that's the number of senators, and the number of columns is the number of roll call votes that were taken in a given year, and that can range from 200 to several hundred. Here's pictures of those matrices over the last 30 years, and you can see that they're becoming more stratified. As we get later on in the years, they are closer to two-party votes, vote by party. Here they are again, and we get up to this year. We don't have all the votes for this year, but we see that they're very stratified. I'm going to take the two extremes there. This is from 1991. You can see that there's a mixture of votes here. Many of the votes are not along party lines. But by the time we're doing it in 2014, most of the votes are along party lines. And if every senator on every vote just flipped a coin, we'd have a random matrix like this. Here's the singular values of those three matrices. At the top is the singular values of the random matrix, the coin flip matrix. They don't decrease rapidly. We can't approximate that matrix by a matrix of low rank. But the other two show the plots of the singular values. By the time we get to the third singular value, we've captured a great deal of the matrix. In 1991, we get over 60%. And by the time we get to 2014, we have over 80%. So I define the partisanship to be 1 minus sigma 3 over sigma 1. This is the amount of matrix that because you can approximate the votes in the Senate quite well by the first two singular values. And here's a plot of the partisanship of the United States Senate over the last 30 years, and a straight line fit to the data. Now, when the data is this varied, the actual coefficients in the straight line can't take seriously, but you can see that the Senate, US Senate is becoming more partisan. Now I realize I'm not talking to American voters here. I would love it if somebody could do something like this for what is the Czechoslovakian version of the Senate. You'd love to see this kind of work. Do you have much partisanship? Here's an example I like to show. This is from Nicholas Troji, who was a professor in Germany when he did this work, but is now a professor in Canada. And if you're interested in what you're about to see, you can go to the website for the Biomotion Lab in Canada and see this. Troji is interested in modeling the human gait. How do people walk? And more subtly, how do we tell attributes of other people as we watch them walk? We can tell their age and their sex and their mood by just watching them walk. How does that work? So Troji gathered data by putting his graduate students on treadmills. They had markers on their body. The motion, these markers was recorded by these cameras in the background. And he would have one subject take a few dozen steps. He'd capture a few thousand frames of data. There are 15 markers on the body that move in 3 dimensions. So that's 45 functions of time, 45 time series. That's what Troji is recording for each subject. So the raw data for a subject is a matrix with 45 rows and a few thousand columns. You want to reduce that matrix, do a model reduction. Oh, here's the data. This is some of the signals that Troji recorded for some of the markers on one of his subjects. If you zoom in on the data, this is what it looks like. It's roughly periodic. That's because our walk is periodic, but it's certainly not exactly periodic, and it's noisy. So Troji wants to have a model of the data. This is a reduced order model of order 5. So it's a 5-term Fourier series, a constant term, cosine and sine of omega t, and cosine and sine of 2 omega t. Omega is the only nonlinear parameter here, and that's determined by Fourier analysis. I won't go into that. But the other 5 unknowns are vectors v1 through v5 that are vectors with 45 components. So that when you form this product of v times these cosine terms, you evaluate this sum. So he reduces his data from a few thousand columns down to 5 columns. And that captures 95% of the motion, something like that. He goes further. Half of his subjects are female and half are male. He takes for each subject, he has some coefficients v. He combines all the female v's into f and all the male v's into m by doing more singular value decompositions. And then he has something called the Eigenwalker. Eigen is the prefix that English has borrowed from German. It means characteristic, or so an Eigenwalker is a characteristic walker or an everyman. The gender is not one of the 5 principal components. So he computes the gender by taking the difference between the females and the males. And let me show you some of Troji's walkers. Oh, that's paused. I'm running MATLAB now. And here they are. Here's the first Boy, somebody is mowing the lawn outside. I hope that's not bothering the audio. Getting too close. Somebody is, here's the first 6 subjects. These are actually the models of those subjects, and you can see how people are walking. Let's skip ahead here. Look at some more. You can see very different walks here. Here's Jamie in the lower right. Jamie's having a bad day, but how do we know he's having a bad day? He's walking slowly, his head is down, so we can tell that about it the way he walks. Let me skip forward to my 2 favorites. Here they are in the lower left, Pablo and Patricia, 2 subjects next to each other alphabetically, but with very different walks. You can see a huge difference in the walk of the male Pablo and the female Patricia. Let's go to the Eigenwalker. Here he or she is. This is the summary of all his data. This is the everyman. And there are 5 components, V1 through V5. I can take a look at these coefficients. If I just stop it with V1, V1 is static. There's no omega term, and that determines the position of the 45 markers, the 15 markers in 3-dimensional space. The V2 term is the basic stride of the walker. The V3 term is a side-to-side sway at the same frequency as the stride. The V4 term is a kind of hopping motion with the arms and feet in phase, and the V5 term is the hands and feet are out of phase. And so you put all those together, and here's the Eigenwalker. Now, as I said, the gender was not one of the 5 components, but I have a slider over here for gender. Let me set that to about 1. So there's walking 1 gender. Can you tell what gender that is? I don't think so. It's kind of difficult. Let me move the slider here to -1, -1. I have to have a better way of moving these sliders. All right, that isn't working. If we overemphasize the gender, we get this. So it's all in the hips and the elbows, the difference between the male and females and how they walk. Where am I? Here's Eigen Worms. These are about nematodes. Nematodes are microscopic worms that live in the soil and help the soil to decompose. We also have them in our body. There are good nematodes and bad nematodes, but they're used in biological experiments. And here they put some nematodes on a plate, heated the plate to make them move, and some ordinary differential equations that model their movement. And the movement of nematodes can be expressed by linear combination of these 4 motions. So nematode motion lives in a rank 4 space. This is a paper out of Journal of Computational Biology, and there's a reference at the bottom. More news, more politics. This is a graphic out of the British paper, The Guardian, a few years ago about Cambridge Analytica. Cambridge Analytica went out of business after this scandal, but this is how it got started. It was started by someone named Steve Bannon and bankrolled by a man named Robert Mercer. And they influenced the vote in England on Brexit and in the United States in the 2016 election. And here's how they did it. This is a paper out of the Proceedings of our National Academy of Sciences by 2 professors from Cambridge and a researcher from Microsoft in Cambridge. And they took their data was, as we now know, Facebook data, almost 60,000 Facebook users. And they looked at each user's likes and dislikes. And that gives you a matrix of 50,000 columns. You then do, these are graphics out of that paper. You then do the singular value decomposition on this big matrix, reduce it to a matrix of order 100 principal components, and then you can take linear combinations of those principal components and predict attributes of all these people. You can find their gender, their politics, their religion, their use of alcohol and drugs, and then more subtle concepts these authors claim, like agreeableness and openness and their age. So these are what the Cambridge Analytica was able to do with singular value decomposition of Facebook data. I can go to the US Patent and Trademark Office and look at patents. When I looked a few days ago, there were almost 30,000 patents that mentioned PCA, principal components analysis, and almost 8,000 patents that involved the singular value decomposition. So these are amazing numbers. They've grown a lot in the last few years. Here's one of the patents. This is from a company called eHarmony, and they have patented their dating service. So it's a method for determining whether 2 people are likely to have a successful relationship. So the BCA is helping find you a date. Here's a recent one. This was just last month. This is by from Korea, and they take an image of your shopping cart at a grocery store or a mall and claim to be able to figure out what's in your shopping cart using principal component analysis and artificial intelligence. So that's patented by these 2 researchers from Korea. Okay, I can go on and on with this list. We see that singular value decomposition is saving the universe, dating, crime forecasting, where's crime likely to happen in your community. We saw image compression. I mentioned Eigen faces is now well established in image analysis. Eigen Worms, there's actually only one paper about Eigen Worms. And then Eigen tissues. I just added this to the list yesterday. A graduate student at University of Michigan heard my talk several weeks ago. And now she's using this in analysis of cancer. Latent semantic indexing is documents and terms, finding words in documents, and finding documents that don't actually mention particular terms, but are related to documents that do mention the terms by the singular values. I mentioned Orly Alter is a friend of mine at the University of Utah who's using the singular value decomposition to look at cancer in the brain. And the MathWorks logo, the vibrating L-shaped membrane. I haven't shown you that today, but if you look at how we compute our logo, it involves the singular value decomposition. Okay, here's my title slide, and I'm going to make low rank approximations to the title slide. And here they are. They're decreasing now, and I get to 1, and that's the end of the talk. So I'm glad to take questions now if we have some questions, any discussion.
Thank you so much for your talk. We enjoyed very much. Now we would like to have a question from the participant. If you have any, please leave it in the chat. So the first one is by Catherine Lund. The question is, although the SVD may save the world and especially computing predictive model by looking for underlying attribute and structure in data, one could argue that such techniques are dangerous at the same time because they tempt people to equate low rank approximation of complex objects with the objects themselves. Do you think we have a responsibility as a mathematician to inform the public of the limitation of such a method?
Sure. Hi, Catherine. Long question. Sure, we have a responsibility. I mean, any mathematical model, like any research, is limited by the fidelity of the model. And artificial intelligence, machine learning have gotten a lot of success, a lot of press recently. There are big ethical problems with the use of those things, like facial recognition by the police and so on. Yes, the answer to your question is a yes.
So the next question is what is important about SVD is we can reduce the size of massively large component matrices into a small one and be able to compute in real time?
Well, the reduction in the size is valuable in computation, but that's not the important thing. The important thing is to get underlying structure, to see what the principal components are, and then look at each component and study that behavior separately. So it's a mapping that reduces the data to a diagonal data set, and then you can study each diagonal element.
Thank you. And is there any other question?
Those two are both very, very provocative questions, and I appreciate having them. Glad to see people are thinking and worrying about those kind of things. Catherine, I'd love to hear from you about what your thoughts are on talking about the limitations of this kind of analysis.
We have something from Professor Strakosh. He wants to ask the question directly, if it's possible. So please, Professor Strakosh, you can.
Cleve, it's for me is absolutely fascinating how this beauty of SVD, not only in applications, but also in mathematical analysis, goes through the decades. And the fact that it is possible to compute the SVD of bidiagonal matrix and certain structural matrices to the full accuracy, that we are able to compute the small single values to the same accuracy essentially as the large single values. I mean, the work of Kahan and Jim Demel and the others. Then could you comment a bit on that? Because I think this is fascinating power of numerical analysis.
Yes, hi, a good friend there. Demel's work on computing the small singular values accurately. That's if you know the matrix exactly. If your matrix doesn't have any errors in it, yes, you can use the Demel-Kahan algorithm to compute the small singular values accurately relative to themselves. But that isn't what we've been talking about here. These matrices, we don't know exactly. And we're only interested here in the large singular values and the principal components. The work you referred to is limited to matrices we know exactly.
We have other question as well. The first one is, do we have some failure example when SVD did not work?
Oh, good question. Well, I guess if you took, I mean, this is a toy example, but if you took if you take the magic squares of odd order, their singular values don't fall off rapidly. Now, there's no point in approximating magic squares by singular values, but the important fact here is that the singular values have to decrease rapidly, and when they don't, you don't get good approximations. I don't know if you can't immediately think of somebody's tried that. You know, we don't often write papers about experiments that don't work. So I don't know if, for example, right off the top of my head about somebody who tried SVD for a data set and was disappointed with the results. I'll look for one. Good suggestion.
And the other question is, it's somehow some personal opinion, I think. It says, which further kind of decomposition or general technique from numerical and linear algebra do you consider the most beautiful for solving the problem?
The most beautiful decomposition. It depends on what you're trying to do with it. There are different eigenvalues. Eigenvalues are important in analyzing differential equations. I have ordinary differential equations. I haven't talked about that. They're beautiful there. Strang has recently made some videos about a new approach he's proposing to teaching elementary linear algebra, beginning linear algebra. Strang is famous for his lectures on MIT OpenCourseWare. But he's got some new approach. It's called linear algebra for everyone, and it starts with something called the CR decomposition, columns times rows, and that's beautiful for small matrices that you study in the beginning linear algebra. I'm about to write my next blog about the CR decomposition. They're all beautiful. They're all beautiful. I'm not going to pick a favorite.
The next question is, could you compare SVD versus multi-layer autoencoder?
Oh, I don't know what that is. Who asked, you have to ask, whoever asked that has to tell me what multi-layer autoencoder is. I'd be glad to know.
So please, David, who asked the question, could you explain further? He said it's a neural network with a bottleneck in the middle. I don't know what is it, but...
Oh. No, I can't explain it. I don't know very much about neural nets. We need to know more about the mathematics of what's really going on inside of the neural nets. They've had amazing success. MathWorks, with MATLAB, we've been doing machine learning and artificial intelligence since beginning when it used to be called the Neural Net Toolbox. Getting a lot of press. I wish I knew more about the mathematics of what's going on deep inside. I think this idea of approximating a matrix by a matrix of low rank is really pretty fundamental. We need to know more about the relationship between, well, the answer to your question, the relationship between what I talked about today and what's going on inside those neural nets.
So thank you. I hope you get the answer for your question. The other one is, was getting into numerical methods such as SVD a necessary part of pursuing other research goal and therefore only pass toward doing something else, or were the methods themselves the goal of your research at the beginning?
Oh boy, you went too fast there. You have to...
I will repeat the question again. Was getting into numerical methods such as SVD a necessary part of pursuing other research goals and therefore only a path toward doing something else, or were the methods themselves the goal of your research at the beginning?
Well, first of all, I'm not doing any research. I'm talking about what other people have done. I'm not sure what your question is getting at. I wish I could see the text of the questions here.
So I think Professor Moler unmuted the participant, and so Peter Haran, if I pronounce your name right, you can ask the question yourself.
Yeah, okay. So the question is only regarding maybe the start of your research career back in the days where you were doing research, whether the methods that you used were actually only like, okay, I need to solve some problem, so I need to come up with SVD or something, or was really the SVD your goal? Like, I want to create a new method.
No, as I said, when I started doing research, the SVD, I didn't know very much about it. So the things I did in research, if you go back and look at the papers I published, the SVD is not there. It's only in my mature adult, as an older person, as a philosopher here, that I really like to talk about how SVD has permeated everything.
And we have a question from Erin Carson. She says, where did you get the music in the background of your SVD video? Any story there?
I don't know. So people have what that ting 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 music. It's the same music that was used in. It's the same music that's used in. Who's the computer game where the plumber jumps from first? What's the famous Mario Brothers? It's the same music that's used there. The film was actually produced by the film department at Los Alamos, and they chose the music. I don't know where it came from. The narrator of that film is actually the narrator that narrated Nova films back in those days. It was a famous announcer. So that little piece of film was a nice piece of work that the cinematography group at the Los Alamos did. And I think it actually won some awards in their field. The question about the music, if you go to the YouTube channel, where the SVD is, where that movie is, you'll see comments about the music as well. Why are you interested? Why were you curious about the music?
So, Erin, can you talk to Professor Muller yourself?
Yeah, sure. Am I unmuted?
Yes, we can hear you.
Hey, yeah, I've shown this in intro linear algebra classes before. The students always think the music is hilarious. So, just wondered if there was some story there or not.
Can I go play that again?
It's very 70s.
The computer is used to simplify the matrix so that most of the entries will be zeros. One method is known as the singular value decomposition. The original matrix is how the computation is carried out. In this three-dimensional representation,
you're talking about this music.
Each pyramid.
Yeah, and in the previous part, it starts out kind of ominous sounding, and, and now it's just like, you know, a happy little SVD song.
Orthogonal transformations will be used to introduce zeros into the matrix.
I don't know.
The initial transformation
I'll investigate
puts zeros
that.
into the first row and the first column. Each transfer.
Do your students think it's hilarious?
Well, yeah, it's, I don't know, it's a happy little song to go along with the visualization. It's kind of funny.
Do you know what I'm talking about when I'm talking about the Mario Brothers?
Yeah.
Yeah, is it the same music that's there?
Honestly, I don't know. I haven't played that enough to say.
I think it is. I think it is.
All right. Well, thank you.
Who was that? Who was asking that?
I'm Erin Carson.
Oh, hello, Erin.
Hello.
So thank you, Professor Muller, for that. And we have a question from Eva. She wanted to ask, can you maybe tell us something about the foundation of MATLAB, initial motivation, or any other story? How do you look back to the beginning of MATLAB? And she said, thank you very much. Many of us really enjoy using MATLAB. I cannot now imagine giving numerical mathematics lectures without having MATLAB.
Well, thank you for the comments. I have given a talk called The Evolution of Matlab, which is my attempt at answering your question. I've given that talk many, many times, and it was getting kind of old. So it used to be, last year my SIAM lecture was the answer to your question. But this SVD talk is a replacement. When I wrote SVD back when I was a professor at the University of New Mexico in the 1980s, 70s and 80s, as just a tool for my students to be able to do matrix computations as a kind of calculator. It wasn't a programming language, didn't have any graphics. We couldn't do graphics back then. Then a controls engineer named Jack Little learned about MATLAB, saw its application in control theory. The PC had just came out, and Little was anticipated the evolution of the PC, and we started a company. I'm the father of MATLAB. Little is the father of MathWorks. If you want to read about the history, the ACM has just recently published the proceedings of a conference on the history of programming languages. It was supposed to be a conference in London last summer. We didn't actually have the conference, but the proceedings came out. So you can go to those proceedings, ACM proceedings on history of programming languages, and we have a long paper there about the history of MATLAB, Little and I.
Thank you. We have other question as well. Have you seen SVD being used in reduction transformation of system of linear ODEs, like in modal analysis, for example?
No. Systems of ordinary differential equations, the model, the beginning model is x dot equals ax. That's a system of linear ordinary differential equations. X is a vector valued function of t. A maybe varies with t, maybe constant, and x dot is its derivative. So the matrix A there maps a vector into its own space. You don't have two dimensions. See, matrix has to be square. X dot is the same size as X. And you have a transition self. That's where eigenvalues are appropriate. Singular values are a transformation from one space onto a different space. Now, if the matrix A is symmetric and positive definite, then the singular values and the eigenvalues are the same thing. But for general A, they're not. And the ordinary differential equations would involve eigenvalues, not singular values.
So thank you so much. Let us thank Professor Muller for his nice and very interesting talk again. And we do very much hope that we can meet him in Prague very soon. At the end, I would like to ask Mark Dostalik to say a few words about the SIAM Student Chapter and introduce the next coming talk.
Well, let me say that I've enjoyed this immensely. They're very good questions, I'm glad to, thank you to the SIAM chapter in Prague for organizing that today.
Thank you for accepting our invitation. We was very honored to be with you today, and it was really interesting for all of us to listen to your speech.